Welcome back to Differential Calculus. In this video, I want to talk about linear approximations. The idea of linear approximations as they are presented in most calculus textbooks is a bit of an anachronism. In today's world, and for the past 40 plus years, we've had access to tools like this, a pocket calculator. This is actually the same calculator I've used for over 20 years now. So it's not exactly new technology. And my calculator is happy to do calculations for me. But calculus textbooks still hold on to the idea of the past. Before calculators existed, before pocket calculating devices were a thing, we needed tools for being able to approximate the values of ugly functions at ugly points. Even something as basic as the square root. Right? Evaluating the square root of 4 is easy. Evaluating the square root of, say, 4.075, I wouldn't want to try to do that by hand. Again, I have a calculator. It will tell me the result. But I want to think back to before that was a thing. Before I get in and actually start doing that, let's talk about why. Obviously, I have a calculator. I can grab my calculator. I can punch in square root of 4.075. It will tell me what the result is. I don't have to think about it. At the heart of that, I know that the function I care about is the square root of x. As you go further in the study of mathematics and the applied sciences that rely on mathematics, knowing that first fact, the function I care about is the square root of x, goes from a given to completely unknown. I don't know the function that I'm going to be worrying about. All I know is some properties at one point. Can I use that to figure out what the properties are going to be at some other point? That's something that we can and will be able to do. We'll get there a little bit later. For right now, let's stick with the simple example. I say it's a simple example, but it turns out that using the limit method for finding the derivative of f of x in order to write the tangent line is very challenging. So for right now, I would like you to take it on faith that f prime of 4 is 1/4. As we go forward in the course, we're going to learn more powerful techniques beyond the limit approach that are going to make this particular derivative very simple to do. For right now, let's not worry about that, and let's worry about what we can do from here. Right? Knowing the value of the function and the derivative at a given point, I can write the equation of the line. Y minus the y point, 2, is equal to the slope, 1/4 times the quantity, x minus the x coordinate, 4. Right? 1/4 times 4 is 1. -1 plus 2 is +1. Y equals 1/4 x plus 1. All right, we can write the equation of the tangent line. Yay. We can even go so far as to graph the function and its tangent line. And we can see that in the vicinity of that point, the function and the tangent line are virtually indistinguishable. And as we zoom in, it gets, okay, it starts to look worse at first, but as we zoom in, it gets better. If we look at a small enough region, the function and its tangent line are indistinguishable. That's the idea behind a linear approximation. Near x equals 4, the square root of x is approximately equal to the tangent line, 1/4 x plus 1. 4.075 is very close to 4. So if I want to take the square root of 4.075 and I don't have a calculator on hand, that's approximately the same thing as 1/4 times 4.075 plus 1. And okay, that's still not easy, but I know how to do long division by hand. I just don't like it. Four fits into 35. 8 times 4 times 8 is 32. Subtract that off, you get 3. 4 fits into 37 times. We could keep going, but let's just stop there. That's good enough. And by using my linear approximation, I get that the square root of 4.075 is pretty close to 2.0187. All right, so let's grab my calculator and see how close I actually got. If I ask my calculator to evaluate the square root of 4.075, my calculator tells me that it is 2.018662. Rounding to 4 digits after the decimal point, 2.0187. To within a fairly high tolerance, those are the same value. So yes, a linear approximation does work, and sometimes it's very, very useful. I apologize for the horrible brightness coming from behind me. That's what's illuminating my calculator so that I can do that. But that's the tool, that's how it has been used predominantly in the past. That's why it has a place of prominence in calculus textbooks. Again, I have a calculator. Why do I need that? The answer to that question is the branch of mathematics known as differential equations. Differential equations is the answer to the question of why is calculus useful. There are other things that you can do outside of that, but by and large, calculus is useful because differential equations describe the world. A differential equation is an equation where instead of talking about the value of a function, you talk about the value of its derivative. And these can become very complicated and they get very difficult very quickly. If you are continuing on in your study of mathematics, after calculus, differential calculus, integral calculus, calculus of several variables, you take a full semester course on differential equations. So we're not going to get very far with it in this course. But some of the simplest differential equations have a form that says that the derivative of a function at an arbitrary point x is equal to some hideous expression. F prime of x, the derivative of f at an arbitrary point x, is given by the formula 1 over 1 minus x plus x squared. If I want to know something about this, If I know that f of 0 is equal to 7, I can use that to approximate f of 0.125. Because I have this function, I can use this function to calculate that f prime of 0 is 1 over 1 minus 0 plus 0 squared, which is 1. Now I know the slope, and I know the point. I can use those to write the equation of the line. I can take that, I can evaluate my function. F of 0.125 is approximately equal to 0.125 plus 7, or 7.125. Certainly, we're not always that lucky when it comes to differential equations, but sometimes we are. And so this is a tool that all mathematicians, all physicists, and engineers keep in their back pockets. This is a tool that is the heart of numerical programming. Being able to talk about the derivative of a function, give some equation involving the derivative, use numerical tools to solve that equation, use that solution to write the approximation of the original function, use the original function to evaluate the thing that you care about. That is most of numerical computational work. And it all starts right here. A couple of examples. We're going to talk a lot about examples of places where the derivative is useful. But before we get into anything else, I do want to mention specifically the example of kinematics, because it's a fairly easy one to understand, keep in your head, and think about that whenever you're thinking about a derivative. If we think about f of x as the position of an object, that's actually kind of awkward to do. In physics, we will generally write this instead x as a function of t. Then the derivative f prime of x is the velocity of that object. Again, in physics, thinking about this in terms of x prime of t is more useful. And just for the sake of mentioning it, you will sometimes instead see this written as x with a dot over it. If you continue onward to study multivariate calculus, I talk about some of when and where the prime or the dot is more useful. And also in physics and engineering, instead of this notation, you will often see this written as dx over dt, which looks like a fraction. We tend to avoid that notation in math when we can, because it's not actually a fraction. But you can do that same thing over here. df, dx, and dy, dx are common notations for the derivative. I don't use them much in this course because they look like fractions. They are not fractions. But all of these various notations are still used, and there is some value. Again, for anyone who's continuing onward to multivariate calculus, one of the things that we study there is you have functions of several variables. And you can have functions of variables which are themselves functions of variables. So if you have f a function of x, but x also a function of t, keeping track of what you're doing and what you're doing it with can be a little bit messy. Are you taking the derivative of f with respect to x or with respect to t? Having multiple notations makes that conversation easier. So there's the value of having multiple notations. The headache of it is I have no idea, moving on from this course, which of those notations you are going to use. I will tell you that for my purposes, for my courses, for my videos, I stick with f prime of x whenever I can in my calculus courses. Physics, I tend to go with the df dx, dy dx for reasons that I will talk about if any of you have me for physics. All right, so there is a picture. There is a tool that we can use. The velocity of a particle at time t is given by x prime of t equals t squared over 1 minus t. At t equals 3, this particle is at the point x equals 5. I would like you to approximate the position x of t of this particle at t equals 3.18. If it helps you, you can think about the position as being measured in meters, the time as being measured in seconds, and the velocity as being measured in meters per second. But this is math class, not physics class. We don't worry about things like do the units work. We just play around with the numbers and hope that somebody else will figure out what it means in the real world. All right, so take a couple of minutes, use what I've been talking about here, see if you can solve this one on your own, and I'll see you in the next video.